you some presentation. Okay. Yeah. Okay. So first of all, if you want to buy like 10 Nano 9K, so this whole set cost just like $25, and this is
I saw a
sufficient to
small one.
start.
Nano is 9K
Yeah,
cells.
Nano 9K. So if you just buy this set, so if you just buy this Nano 9K, but you have to solder it. If you don't want to solder, you can buy 10 Nano 20K unsoldered. And then you can buy LCD screen, and you can buy TM1638. So this is one way of doing it. So you can buy just those 3 pieces. And the good thing about this platform is like a fast synthesis, low cost. Now, if you don't want to solder,
No, I can
and
solder. It's not a big deal. I mean, I'm pretty much okay. Jurassic is expensive, light, especially that's a Max 10, right? That's
no, look, I'm not talking about D10 standard. I'm talking about D Lite, which cost like $150 maximum. So this is another board. It's more expensive, and it's not necessary to get this one. But I want to mention it because this board has the least number of problems. Yeah, and now so there is this board. Then if you go to like AliExpress, there is a board um, called Sailings, which is inexpensive. One second. So if you look here, Cyclone 4. Yeah, so this is a book because it's inexpensive, and it has everything. So if you want, you can buy this board. So this is just like less than $50 board. So let me give you a link to the chat. But recently I am trying to switch everybody to this Tank Nano because I bought like 30 of them for seminars in like different places. So we plan like a seminar in Mexico and in other places. And for this reason, I am switching everybody to Tank Nano 9K. But for Tank Nano 9K, you need to buy additional components. So let me put into chat this. So let me put into chat this board. So this is one choice if you like Altera. Now, if you want to buy 10 Nano 9K, you can buy 10 Nano 9K. So I have all links from this post. But then you need to solder header to 10 Nano 9K.
yeah,
But
they're
even,
on Amazon, I think, as well. I
yeah,
saw them in
they
65
are
as well.
like on Amazon as well. Yeah, but in order to do meaningful exercises, you need to buy TM1638, which is which like adds buttons and 7-segment display. Okay, so here is the post. Okay, now like if you buy this set, which is TM1638, then female jumper wires and this LCD screen, like you're pretty much offset, like all set. Yeah, so the recommended is is a Altera board or this Tank Nano 9K. With Xilinx boards, there is a very annoying feature. With Xilinx, the synthesis is too slow. So basically, every time you change your code, you need to wait for like a minute or more to synthesize everything. And this is very, very annoying. So with Tank, it's seconds, and with Altera, it's like 20 seconds, but with 10 nano, it's like 10 seconds. So it's very fast. Yeah. Okay. So now let's go to the basic introduction. So most of people saw this basic introduction. Hi. Yeah. Just a moment. Let's actually meet. Yeah. You can sit here. So wait. You are your first time here, right?
JC?
Yes,
Nice
yes,
meeting
yes, 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 yes. So we met on Maker Fair, right?
Yes.
Yes, yes. Okay. Yeah. So yeah. Usually, like people are like slowly coming here, like before noon. But anyway, so can you before we continue? So like I'm going to give introduction to a new member, but maybe you can tell little bit about yourself. So what you are doing.
My name is JC. I work at NVIDIA. I started as an ASIC designer, but I left for software programming for a few years, and now I'm like a hardware architect.
Oh, okay. Yeah. Okay. Yeah. So let me just tell like various things. So we are doing with this group. So some people are coming here, and some people are doing like doing this online. Yeah. So let me show some basic presentation. Then we start. And then we start from there. So what you're saying is that you were doing like a lot of like microarchitecture and RTL coding before. So how much? So what was the largest design?
Actually, I'm now working on like a low-level software.
Yeah, yes, I understand. But what did you do before when you did ASIC design?
I was working on like a video codec.
Mhm.
What else? Power management. Deep learning accelerator.
Okay, so this was all in NVIDIA, right?
Yeah.
Okay, yeah. So basically, let me give you some like basic uh, basic idea of types of projects we are doing. So we have several repositories. So one of them is called Basics Graphics Music, and those are those are introductory examples. And so basically in those introductory examples, so let's make it larger. So in those introductory examples, it starts from like from zero. So it starts from like gates, then like proceeds to like counters, shift registers, and things. Then, but we also believe that in order for people to make studying to make learning Verilog interesting, we connect this to exercises with the graphics. And you probably saw on Maker Fair this my exercise. Yeah, with LCD.
For array of
Yeah. That array, but we also do this with LCD, so you can actually like try it with LCD. And basically, what we are doing, we created support for multiple graphics controllers, starting from like VGA, HDMI, LCD, and so on. And one moment. Yeah. Yeah. So basically, what we do is that we have a user module, which is like a lab top. And we have a graphics controller, and this graphics controller gives to user coordinates X and Y. And the user module generates RGB, which we send outside, FPGA together with the signals from this graphics controller. So this graphics controller for like VGA and LCD, it produces like VSync, HSync, and for HDMI, it has a bridge which produce a differential pair. But basically, this is isolated from user. So all user does is user starts from a basic exercises, and for example, let me show this in a VS. Or let me show you here. So for so user starts from basic exercises. Like let's get example from like Maker Faire. So user starts with exercise that he just uses combinational logic to draw a rectangle, and then we like add like box to generate strobes, and then people can create their own games. And so basically they're doing something on the screen during the very first day they study Verilog. So now for this basic example, we have support for like approximately 40 boards. So we have like bunch of boards like Altera, Xilinx, Govin, Lattice boards, and we support multiple tool chain. And if you get, let's say, like let's get this like Tang Nano Govin board.
Yeah, I got one in my bag.
Yeah, so basically we have a board specific top. Oh wait, this one. So we get a module board specific top, which actually connects board specific signals to this like idealized board. So we have here some like glue code, and user usually don't see it, but the presence of this glue code allows us to isolate everybody from like boards, from tool chains, and so on and so on. Now, yeah, so basically our first claim to fame is that we can isolate learners from a vendor. Yeah.
So basically you create a framework so that user can focus on the IP design.
Yes, IP design, not like things about details of like peripherals and graphics and so on. Now, this is the first thing. So second thing, you can see that most introductory examples, they have just like buttons and LED and stuff, and most introductory classes in universities, they go to the like finite state machine. Then there are some classes where they teach like 5-stage MIPS pipeline or RISC-V pipeline. But finally, when people come to me to like a job interview in Samsung, what I found is that they are not trained well on questions about implementing pipeline blocks with like a flow control, things like this. So because basically see both in like Samsung, Nvidia, Apple, in AMD, everywhere, when you get RTR engineer, you want him to implement like pipeline design of some nature, like in like GPU fixed functions, also like graphical primitives. In CPU, it's a pipeline CPU. In like networking chip, you also create like a pipeline and FIFO for to process piece of chip, and same thing in design you mentioned. So our like next claim to fame is that we one second, just want to see okay. Yeah, so like our next claim to fame is that we also have examples that show microarchitecture, which effectively train students for microarchitectural questions. And we have such examples on the board. So with like different type of like pipeline and like and FIFO and so on. But we also have it in another repository called System Verilog Homework. So if you go to System Verilog Homework, you can see it has various like tasks to that effectively starts from zero and train student up to the level of a job interview. Yeah. So one example here. One example here is like if you go to we actually show you it's in a graphical form. Just I need to find where. Yeah, it's here. So homework 2. Yeah. So one thing what I found students do not do well on job interviews is the following question. So suppose you have a actually use this one. So suppose you have like a pipeline module which implements like square root. Okay, so we just has a fixed latency. So we have like a bunch of things which do like a fixed latency, pipeline. Now, so like basically you just put like argument x, and after n clock cycles you get a result. Now, first I usually ask some like easy question, which is can you like calculate formula of sum of 3 square roots, so square root of a plus square root of b plus square root of c. So they usually put just 3 blocks pipeline, which works just fine. So which is fine. Then I ask yeah, so like basically you put 3 arguments, and after like n clock cycles you're getting a result. Then I ask students a question. Suppose you have only one square root module, how can you do this? And they build a finite state machine, so which is fine. So students, they are trained to build finite state machine. Then I ask them that suppose you have like then as that what if you have like 2 such blocks, so how can you improve latency? And then ask like I may ask how can you use in your finite state machine the fact that your module is pipeline, but also like minor details. What I do next is ask them that suppose you have dependency in your formula. And suppose you have square root of sum with square root, so you need to compute one square root first. And now, how can you make computing of such formula pipeline? Yeah. So here first So here first I ask first, like they says that, oh, you can just modify finite state machine, but it says that if you do it in finite state machine, you cannot put argument every clock cycle. So can you create a block which accepts argument every clock cycle and makes argument and makes result every clock cycle? And they start to draw something like this. So they put they first compute C, then they add B. But the problem, like I show them that by the time they finish computing A, B is long gone because B is already overwritten by like other arguments.
Right.
So then they start to ask like, oh, can I make the square root of combination of blocks? And I said, no, this is too much easy. And then there was a student who was saying that, oh, I learned in school how to do a Tomasulo like out of order CPU, and can we use it here? I said, using Tomasulo every time you need to build a small fixed pipeline is like overkill. So then I asked them whether they learn about like shift registers or FIFOs or like circular buffering. So they, yes, we did. So and then like students actually realize that they can delay B by using so then it says that, did you learn a shift register? They said, yes, we did. They said, oh, yeah, I can use shift register and just put the shift register to delay argument. And some of them are saying that let's put a FIFO or let's put circular buffer. But what I found is that majority of students actually do not do this right away. So there are minority of students can figure it out right away, but majority do not need some time for it. And not only that, then I ask them questions how to put flow control with the back pressure. So how you can add back pressure to it, and they are struggling with the back pressure questions. One of back pressure question is that suppose suppose you have a block suppose you have a block which has like two inputs A and B, and it adds A and B number. So like each of them is a bus, like is a white bus. And suppose you like you need to add those numbers and generate C. However, each such port has a valid ready interface. So here is a valid interface, and here is a ready, and B also has a ready valid interface, and C also has a ready valid interface. And so just write a Verilog code which implements such device. So you need to add numbers. They may come at different time, and you need to add them back to back if they come back to back. And apparently many students struggle to do this, and even from like top schools, because they are not trained in the school how to do flow control, and they're not trained in the school, what is worse, how to verify their design. So they write only very primitive test benches, and when they make mistake in such design, they cannot figure out that they made mistake. So for this reason, we put examples how to make like self-checking test benches and how to solve such a task. So like another variant of this question is the gearbox, where you have like narrow data stream and you need to produce wide data stream, like 2x wide, and you have also like valid radio interface. Also, apparently almost nobody knows about credit-based flow control. Also, like in all like electronic companies, it's widely used because in like Stanford and like MIT, they're using a textbook which was published in 2012, and it was using the art of maybe year 2000. And in the year 2000, pipelines were implemented with like double buffers instead of credit-based flow control. So yeah, so we have examples of this nature. So our most recent thing, what we did most recently, and this is something which is in play today. So this is not really went out. Is back in August, I met with David Harris, who is a professor in Harvey Mudd in like Southern California, and he is actually author of a book called Digital Design and Computer Architecture. So he is now writing another book, and his new book. So just a second. So his new book is so Elsevier Paris RISC-V SoC. RISC-V microprocessor system on chip design. So this book is supposed to be published on January 1st. And what he did in this book, he shows step by step how to like implement a RISC-V CPU capable to run Linux. So the CPU also it has fixed like classic 5-stage pipeline, but it also has TLB MMU. So this has virtual memory, this has caches, and he put the whole thing in detail about, for example, FPU. And the source code for this thing is available on the web, and this CPU is called Wally CPU. And here is the structure of this CPUs. So this is the pipeline with FPU units. And then in his book, he goes in all the details of like implementing FPU, implementing TLB. And if you look to his like table, he talks about verification, and he talks about implementation, prototyping on FPGA. So he goes like in all the details. So practically he put into book same thing what happened in a real silicon design team, but in sort of miniature.
But it seems to me the Verilog language itself has migrated a bit, well, from the previous version.
From Verilog 95 to system Verilog. No, but
Not much.
mhm.
I think that the bigger gap might be from, well, the RTL design issue you just mentioned for sure. But after you have the RTL design, the verification tool set is completely different. Instead of like iVerilog, those kind of a pure software simulation, you only verify about functionality, right? Not complete even. You have to worry about equivalence check, for example.
Formal tools, yeah.
You have to verify timing. Also, you have to, besides the basic functionality, you have to worry about those built-in self-testing for testing functionality. Right? Sometimes those are, how to say, probably consumes as much time as you verify what the functionality you have in mind. I guess those it's very hard to be taught in school. Basically, you need a real
Mhm.
kind of a migration of the design
Yeah.
because you are building the real chip, right? When the,
Yeah,
the system comes back, you have to do all the testing.
First of all, like timing, about static timing. Just so can you hear us from this microphone? Can you check? Yeah. First of all, speaking about static timing analysis, certainly when we show them microarchitecture questions, we absolutely must tell them all the things about static timing analysis. Building pipelines without knowledge of static timing analysis, like principle of how like synopsis prime time
Yes.
gets critical passes, it makes no sense. Because this is just like studying electricity without magnetism or magnetism without electricity. This all goes back to back because designer has to build pipeline by like evaluate timing. So this is the reason why we put exercises not just with simulation, but with FPGA boards. Because with FPGA boards you have time. But in addition to it, we also have in our example use open lane.
The eFabless.
Yes.
Yeah, I saw
Yes,
the
eFabless
online.
uses
That's
open
very
lane.
interesting.
So I can actually show you how this all looks like, because we have eFabless uses it in like for like tiny tape out, but we also have example how to use how to do like ASIC synthesis with the timing.
Okay.
For a simple toy like CPU, which we use as an example. So let me just show you screenshots for this thing. So if you go to projects, so basically when we teach people about CPUs, first we start with teaching them like assembly language and simulation on like level of instructions. Then we show how to like simulate simple programs. Then we show how to simulate in like Icarus Verilog in like on RTL level, and then we show them how to put this on FPGA board. So you put like IP and put on FPGA board. Then then we show this design running on FPGA board, and they can demonstrate it on the board. And but then we show them how to synthesize it for ASIC. So yeah, so far it's FPGA, and then we show them how to use open lane to create a simple floor plan, synthesize it for ASIC. And when we do synthesis for ASIC, we show them the whole bunch of report, including from static timing analysis. So if you go here, let's see, do I have this reports right now? ASIC config. So this thing does produce bunch of static timing analysis reports. So let me see if I have this report saved somewhere. You want to beginners. So let's actually start running this while we are talking, and you will see what kind of report it produces.
So this is third-party open source backend toolchain.
Yeah. So what happened? What happened is there were some like open source like place, route, and so on tools, which were made in like last like 20 years, but they were all very junky quality. So they usually combined with like a synthesis tool from Berkeley called the ABC, and then with front-end USS. But several years ago, DARPA created a plan to like invest into open source EDA tools, and they did grants to University of California, San Diego, which made a tool called Open Road.
Okay.
And together, this open lane and open road form a tool chain, which is good enough to be used for such simple design, for like microcontroller type of design. And then they combine with the eFabless. So I have a slides about it. So let me actually show you slides. And so now you have the whole tool chain. You can demonstrate all the things like a static timing analysis and place and route and go all the way to the GDS2 file.
Yeah.
And if I'm not sure whether they cover this like self-test or they must have BEAST.
I see online they have like a big wafer. On the wafer, probably at the very outer side, they're gonna have the BEAST built in for every call for you. So you just reserve like interfaces to be connected, and they probably can do the testing for every how to say.
Yeah, so this is for tiny tape out. Let me actually open slides. So for some like another person who like joined us, I will also go first through simple slides. And so something which is for you probably trivial, but I will do this fast. So let me get, for example, these slides I was using in LA. Seminar there. Okay, so yeah, so those are boards we are using, and this is our typical setup with a high-end board. By the way, this board is sufficient to completely synthesize a microcontroller type core capable to run Linux. So this has 138,000 cells. Yeah, and we have another examples like a microphone and LCD screen and so on. Now this is our simple setup, which is enough for running simple CPU. Yeah. Now, yeah. So now, if you want to make this is by the way open lane flow. So let me actually start running this flow while we are talking. It runs slower, but let's go to school RISC-V. So open an integrated terminal. Actually, yeah. So now we have a bunch of scripts, and some of those scripts synthesize. What you synthesize for ASIC. So in order to synthesize for ASIC, actually, I didn't run it for a long time, and this is kind of intermediate version. So this actually may not work now, but let's try. Maybe it will. So this is a script which isolates user for all the flow in open lane, because this has like some make files and tickle. Okay, so this does have error. Okay, running very later 3 errors found. This is probably error in something recently added. Oh, I know what to do. What we are going to do, we are going to switch to some another branch.
Working version.
Yeah. So git switch new graphics. The branches behind origin new graphics can be found for local against the git pull. Okay, now let me just briefly check I don't have any extra unnecessary files here. So okay, now git clean. So let's uh, um, what is here? Oh yeah, here is probably temporary file. Anyway, so let's just clean this thing. Okay. Now let's go back here and run here async synthesis. So here I want to close everything. Demo. Okay, so let's see whether this version works. Yeah, so this like does no, this version also doesn't work. Yeah, I should not fast forward it from that version. Anyway, this thing you can see the same thing in a tiny tape out.
Mhm.
Because if you go to a repository I did for tiny tape out, for example, this is a repository which we did using our examples we do in a Verilog. So in tiny tape out, you just put all your source code in some place, and you put a description of your project, and you put your desired clock speed, the clock frequency, and it makes some basic floor plan by itself, and then it generates bunch of reports. So it runs everything as a GitHub, GitHub Actions. So now, if you go to Actions, you can actually see what they produce. And here is action test, action documentation, action GDS. So this is what we need. So we are going to action GDS. And here we have GDS summary. So here it shows some number of ASIC cell it is using. You see, and then it gives you all the listings. So let's get artifacts. So let's get GDS logs.
There exists a template of constraints, so that you only need to provide your Verilog file. You should be because the interface are standardized in a way, so that you only need to provide a design, and by leveraging the templated constraints, either by a synthesis or place and routing, and it will report to you, oh, this works or not. For example, if you have a too high clock frequency constraint, you will say, oh, I cannot do it with this. Okay, I got it.
So they have essentially push button synthesis where they write their own tickle script with create clock and with setup and hold and all the stuff. So user doesn't have to see it.
Okay.
So now if you go to report, you can see their timing report. So let me find their timing report. It's in downloads. GDS logs. So GDS logs, ZPR runs. Yeah. So if you go to if you go to runs, yeah, if you go here, you can see all steps in synthesis. Yeah, so if you go here, you can see all the steps in synthesis, and we can find their reports. So let's find I think it's called I think it's called STA something. So find grep STA grep RPT. Give they call the they do have reports. So you see, they are doing so let's find static timing analysis report. Skew max. Whether they have quality of result. Yeah. Here is the worst negative slack. Yeah. So you can get like this report.
A mean condition, max condition.
Yeah. So, but let's see whether they have quality of result. No, they don't. So let's see this thing. Yeah, but here was here hold is 0, but there is no negative slack in this design. So I'm just trying to find STA complete report. They might have this report in final. Yeah, let's see final. So final SDF, okay. FGDS layout. Okay. grep-r find RPT. No, they don't have report. Okay, let's see. ST. So do they have? Okay. Yeah. So they have STA in a PNR. Config check state out violator. Let's go here and see their main report. So power, yeah. So they put some like power. So I have no idea how they get dynamic power. Okay, max, mean. Here, critical path. You see? So same as if you run Synopsys and Cadence. So students can use free tools.
But the problem with this, because they are running against the templated constraint file, right? If they see like a negative slack, how can they modify the constraint? Because you must know the tool pretty good. In addition to your design, before you can modify.
But if they see negative slack in this report, what they do is that they go to critical path because there are signal names.
Okay.
And they
modify the
they just modify their design.
Insert split the long path into multiple.
They split long path because they can relatively easy guess signal names from this critical path report, and then they either like optimize their combinational logic or they split long path with the registers. So basically, you can use this tool to teach people how to split with registers. So basically, our approach is that first they play with FPGAs purely like functionally, but then we quickly tell them that like FPGAs also have static timing analysis, and we show them where is like maximum or minimum or something. In fact, let's run it in FPGA with something. So let's get the same design. Let's do git switch to the latest. Okay. Maybe the latest also ASIC in this one.
Too slow.
Yeah.
Too easy, I should say.
Yeah, it's let me close everything which is unnecessary here. Okay, so while we are talking, okay, so let's actually synthesize something for FPGA, and I show you how it shows in FPGA. So let's go to basics. Let's say like shift register, the simplest one, and then we. So in our flow, we first choose FPGA board from a list. So let's get like Altera FPGA board. So let's get like G0 Lite, which is board number 17, and then they run synthesis, and so first they learn about like static timing analysis in FPGA. Then they do microarchitecture exercises. Then they learn static timing analysis in ASICs, and doing open lane. Like of course, yeah, with a formal verification, it's so difficult because there are no free formal verification tools which support SVA.
Relative simple design, you probably do not need that.
With relative simple.
Use like a traditional functional verification should be good enough.
Yeah. Now let's. Oh, okay. So now because it's not connected, so now if you run like GUI for FPGA synthesis, it runs GUI, and here.
Well, but for like this kind of a tool, you need a special license from.
No, this is actually free version.
Okay.
This is education. FPGA vendors, they usually have educational version.
I see.
And all our examples work with a free license.
Okay.
Yeah, a commercial license for Quartus costs like $5,000, but we don't need it for like our examples.
I see.
Yeah. So now, if you run like even educational version, it does run like a timing analysis, and we will see now report from a timing analysis. So if you go to so you can just view a report. So you can see here like Fmax. So they don't have here negative slack in this report, but they have Fmax. So and the good thing is that they can use like netlist viewer, and in this netlist viewer they can actually see what we synthesize. Yes, the reason I'm running a Quartus because it has the best viewer. So you can actually go to lab. I think we run just the simplest design, which is so what is this design?
Shifter.
It's like
it's a shifter.
It's a shift register design. Wait a second, was it shift register design? Because it shows only one gate. 1 second. Yeah. So you see, this has a counter to make a slow, to make enable signal, and then it has a shift register. So students actually can learn a lot with FPGAs, but they cannot learn like ASIC timing. But then they can learn ASIC timing using open lane. And kind of reports OpenLane does is close enough to what they see in workplace with synopsis and with cadence tools, because they also, most recently many people start to use synopsis RTL architect, which is a physical aware tool for front-end engineers. So you can see in that tool better connection with like probing from schematics to your source code. Yeah, but even here, by looking at those reports, they can still figure out problems in timing and learn micro architecture. Yeah, but now I wanted to show you why we are using this this book. So if you, if you go to this open core, you can see that we actually don't need to use the whole core. We can get pieces from FPU, for example, because we have the whole source code for this FPU. So you go to like FPU, and this has like fused multiply add and like square root and so on and so on, and we can use pieces of this design. So we can use pieces of this design to create our own homework exercises. And this is what we started to do recently. So you see, this has also like details of floating point arithmetic with like not a number, overflow, and so on. So most recently, and this is something which is going on right now, I will show you. This is a volume.
Yeah, no, that's one. Did anyone successfully put the FPU into your training?
Yes. We just did it recently. It's like Mike Kuskov and me. We all put. So I will show you this result. It just started to work like yesterday. So if you go to our repository for homework exercises, what we do is, so let me actually pull this repository. 1 second. Huh?
Something else.
Yeah, it's just like something recently. Just a moment. How to?
This problem seems like trying to take the driver from Linux and putting it into Unix.
Just a second. 1 second. I just need to git pull, and I will show you this thing.
So you're indicating it to give it a CPU?
No. Look, I'm not in. Look, I'm getting pieces of CPU and then use it not as a CPU. I'm using it just to create just to build fixed pipelines for computing formulas.
And then run the test bench for
And then run test bench for this formula. So let me show you. Look, I will show step by step. You're like jumping ahead. 1 second. I just need to get this most recent token because it's private repository. Yeah, okay, so now let me put back screen sharing. Okay, so now what we do is we have like all exercises. For example, for example, we have exercise that suppose you have as a black box comparator. Think we just compares two numbers. We show example of a code which instantiates two floating point comparators and then creates simple max to sort two numbers. Then the next exercise is that how to sort three numbers. So student has to write this module, and then we have so we put here a task, a problem for a student. This is a solution. So you need to instantiate three blocks that compare number, and then put a more complicated multiplexer. And then we have a self-checking test bench, which simply sorts three numbers in the system Verilog and compare a result of module against expected. Now, how do we get pieces of a Valley CPU? We don't copy it into a repository. Instead, we have a script which runs all examples. We just clones it from the web, gets pieces from it, and makes the homework using those pieces. So we are effectively using pieces from open source CPU in order to train students how to build finite state machines, pipelines, and do like computing devices with a back pressure. So now you see, in like many schools, when they teach students how to do like finite state machine, they put like some like a traffic light controller or some like some toy examples. But from my perspective, because students go to like companies like a Samsung or like NVIDIA, where they work on like real work, it's better to give them a realistic examples. And this example is a realistic.
There's one other, I shouldn't call it problem, but it is a fact. It seems like the academia world, they are now, especially from Berkeley, because they use this software notion to create design instead of, and that, in my opinion, unnecessarily make the whole framework too complicated.
No, yes, I completely agree. So they created teaser. And
Exactly.
teaser, it's a language based on Scala.
Yeah.
Yeah. So but there is only one company which like adopted it completely, which is a sci-fi, and basically what I heard from a sci-fi. So because like all the CPU people, they're moving around companies. So what they're saying is that when new engineer comes, he usually spends several months of learning teaser, and teaser helps in doing problems like if you have interconnect with a complicated interconnect, instead of putting glue logic manually, you just put it in teaser, and teaser automatically generates all the interconnect logic.
But that only solves the interconnection.
Yeah, but this one solves interconnection. Then they also, for fixed pipeline, they have the same teaser code which implements either 3 or 5 stage pipeline. But you see, this is not enough to make it value. So like other companies do not adopt it really.
Well,
Or like did NVIDIA adopt the teaser?
no.
Okay.
Well, in my opinion, well, maybe because I'm the last generation already, so I do see a gap here. I understand why they come up here because they are trying to attack the problem from a software mindset. Let me say that.
But this, what they do is not a software, because if they want to like do a high level synthesis, it's like different story.
They try to use the new fancy modern language features to generate a design in a way that you just mentioned.
Yeah.
Well, it does a good job for that problem, but that's only a tiny problem in my perspective. You only solve the interconnection. Well, in my days or earlier, we used the Perl to resolve the interconnection. Nowadays, Python.
Some companies still use Perl. There is an embedded Perl, and this code is alive and well.
And the problem with that is, unlike software, you patch every day probably. For our design, the IP gonna lives for probably 20 years before you really, how to say, modify it. Well, you do modify it, improve it here and there, but once it's ready, we seldomly modify it. But because
Yes,
why? Then what's the point?
Same thing is like AMD and MIPS and so on. So this IP lives for like decades. It's for sure. But both Perl and Teaser are effectively fancy microprocessors. And just there are people who are just too lazy to study like generated system Verilog. So they say, oh no, I don't want to study generate, but I already know Perl or Python or and like they use embedded Python to generate
yes.
to generate things where simple generate would work.
Well, why I shouldn't say, it's sort of like I complain about this because I would like to use the Berkeley core, right? I can, if they generate as a Verilog file, it's easy for me to adopt.
Yeah.
But now I have to study tons of time to study this whole, how to say, software stack or framework before I can even debug.
But see, a sci-fi company which uses Teaser, they sell to their customer not Teaser. They sell to their customer Verilog generated by Teaser. Yeah, I personally in our activity, there is one person who like Teaser language, but we don't have a goal to teach people either like Teaser or derivative of such methodologies, because our goal is to make people who can pass interview to large electronic company. And for this reason, this Teaser is totally out of our way. But we do want to use a realistic code, and this code for this open hardware created in academia, it's not the best code, but this is rare enough. This is real enough to approximate what they can. You see, for instance, here is a task: write a finite state machine which uses just one instance of comparator to compare. And they can do a finite state machine using this example. So they can put arguments to comparator, check the result, and so on and so on.
I just feel pity because the Berkeley created such good design, right? It's
Boom. You're talking about Boom. Boom
whatever
design.
the RISC-V derivatives from.
It's called Boom. Yeah,
but
it's a super scalar out of order.
The problem is it's hard for me as if I work on the open source world. It's very hard for me to use that, right?
Yep.
Because I want to modify here and there. I need to modify the Chizo source file instead of Verilog.
Yeah, but let me very briefly. Yes, we are working on from elementary to advanced. So let me switch back. So because so we have another person who joined online from Canada. So wait a second. What is your name again?
Oh, sorry, Evgeny.
Yeah, Evgeny. Yeah. So Evgeny just joined from Canada, and I will now show some introductory things to him. But you can see, maybe you can also tell us something about this. Yeah, because basically here is a presentation I usually show to people. So basic strategy what is that we create elementary examples. Those examples are now used by like 20 something universities, because for them it makes sense, because they don't really like vendor specific examples, because vendors just
Try to sell.
try to sell, yeah, they want to sell their boards. So instead of teaching students how to design, they teach some details of like Xilinx DSP48 block, because they want to just do vendor lock.
Yeah, sure.
Okay, but we are doing without vendor lock, so we like allowed to switch between different tool chains, and we also provide exercises in like connected to like graphics, music, and connected to like job interviews. Yeah, this is kind of basic idea. And to do this, we actually work with some people who sometimes come from software companies rather than hardware companies. And then they go through our homework examples and through our like basic examples with FPGA boards. And once they get more experience, they help to create other examples.
Okay.
So this is so basically we just grow a number of people who contribute to those projects, and you can see that this basics graphics music, which is like basic exercise. So it had, so this has like 43 forks, and he has like many of like 31 of contributor. Plus there are people who are not in this list, but they contributed to predecessor projects. And then like I have a hobby to go to different countries and make something there. And we actually use those examples. So not only here, but we used like this year, like in like Azerbaijan, before this in like Georgia, before this in like Central Asia, and like in Russia, this is very popular. So they have a bunch of schools using it there. And we are planning actually with Jorge. So Jorge just went to different room. We are planning seminar in Mexico. And there are many places in Mexico who are actually interested in learning this thing. So for such exercises, we use a simple FPGA board like this this set, which costs just like $25.
Yeah, I bought.
So
one.
yeah.
I bought one myself.
Okay. So you can like play with you. Yeah. And now basically I created this into.
Fine.
So what? Yeah. This one.
Right.
Okay. This time frame 25K. Yeah, you can use a 25K. Yeah, I can show example with a
Well,
25K.
I don't have
Very
anything
good.
set up.
No, but I have the setup, so you can connect and you can set it up. I will show you how to set it up. Now, but this like basic, this is the most like basic set is for 9K, which cost of it is just $25. So you just like put those things together and they all work. And then we'll show you how to connect your thing. Yeah, this is just smaller FPG, but with the 25K, you have more options. You can actually put the even core which can run Linux because it's large enough. With 9 yeah, because remember when we put NIPS microactive UP into FPGA, 20,000 cells were enough.
How much is the 25K?
25,000 cells.
Yeah, how much does it cost?
How much does it cost?
25.
This is about
30
bucks?
30 bucks.
Yeah.
Something like 30 bucks, yeah. Yeah, okay. So now, but so we have this type of examples. Now let's go back to Evgeny. So Evgeny, so you're probably bored from our talking because we are talking with NVIDIA architect who was RTL designer, so we jumped ahead. But for your basic understanding, so here we are talking about methodology called digital design on hardware using hardware description language, which is used for last since like early 90s to design everything. And I'm showing here NVIDIA like as an example. And basically, yeah, so here you design, you have like hardware, software, and in software you start from program like C and you create chain of machine code. And with the hardware, you start with code in Verilog, and you create such graph of logic elements, and then you map it to create a GDS2 file, which you send to Silicon Foundry. So here this module has input clock, input reset, and it has output like a 2-bit vector of output. And now what it says is that always when positive edge of clock, so when clock changes from 0 to 1, if it's reset, we assign to 2-bit D flip-flop value 0, and otherwise we increment its value. So we are essentially creating a counter by doing this code. And basically all digital design is basically a combination of combinational logic and state registers. And then here I'm talking about basics of combinational and sequential logic. So in combinational, you just put like some values on wires, and then you get output after some number of picosecond. But with combinational logic, we need to figure out when we are going to get result, and for this reason we use clock. And with sequential and combinational logic, we can build like finite state machines. And so this is counter animation. Yeah, and then you can manufacture it on a fab or with tiny tape out process, or yeah. So here I talk about how Silicon team is organized. By the way, this is a block with credit-based flow control, which students usually don't know after school, because this is very mainstream in all the Silicon companies, but students simply don't learn it. And it was introduced recently by a professor in Cambridge into a textbook, but doesn't have examples. So we provide examples for this thing. Yeah. Now, so what is FPGA? Like FPGA is just a matrix of, wait, didn't show here. Yeah, okay. So basically with ASIC you can do high volume applications like cell phones, where like you need a performance and you can afford to do initial payment for commercial production. But if you want to prototype something or to learn, then you can use FPGAs. We are using FPGAs for learning here. And basic idea how FPGA is implemented inside using lookup table. So, Evgeny, if you go to website, you can get links to all those presentations. Yeah, and here is a Harris textbook which explains this thing. So in order to work with our examples, you need to get Harris textbook. And
is this a book to be published?
no, this is actually previous book. Oh. This is a basic book, and the next book is more like advanced. Yeah.
Can I
Now,
copy the PDF? So-
we can print it to use inside here because it will, yeah, we will do it later on, but because the book is coming out in like March, so it's like David wrote. So, but we can like circulate it like within our group just to work with that code. I will show you that code. Yeah, this is textbook which is used in Stanford for microarchitecture, but it doesn't go far enough to the credit-based flow control and so on.
Should
Yeah,
I
and
worry
this is
about
a new-
this? Sorry.
Huh? Just a second. This one? You have a question? Evgeny? Did you ask something? No, I'm not on mute.
Sorry,
Wait.
I'm mute.
Yes, you were on mute. So
Yeah,
what is your
sorry.
question? Yeah.
Okay, sorry. So that Delian Harting book, should I pay attention to it or just switch to Harris Risk 5 book?
No. Daily and Harting book is actually pretty good. It
Okay.
has stuff which original Harris and Harris book doesn't have.
Mhm.
So this is good book to have. A new Harris and Harris book is good if you want to go deep into CPU. Like
New
Linux
one, which
system.
is for 2025, right? That's for May. That's on the
Yeah,
website.
yeah. So what I recommend you at this moment to just stick to studying digital design and computer architecture.
Mhm.
And so what I recommend is the following step. First, you get this book and you read, you can like skip read it until chapter 4, and then you read chapter 4 completely.
Mhm.
Because chapter 4 has description of system Verilog.
Mhm.
Yeah, so first you learn basics of system Verilog language. At the same time, while you're doing this, you will get introductory board, this FPGA board, and you run basic examples. And this like article in Verilog Meetup has a instruction at the end how to install software and how to run everything. So
Okay.
we even produced this instruction in Spanish, Russian, Ukrainian, and
Okay, okay.
Belarusian languages. So in 5 languages. So when we go to Mexico, we have instruction in Spanish as well. But you go to this post and you get this thing. So it shows how to install how to install Govin software for this board, and you can install it either on Linux or Windows, and then it shows how to assemble wires on the board. And you don't need to buy microphone and sound output right now. You can just buy LCD screen, 10 nano and TM1638. And then it shows how to run examples using scripts. Yeah. So this is how to do examples. Yeah. So first you get this board and you use Harris and Harris as a theory, and you read this instruction how to start running examples, and then you go through the code of examples, and starting from very basic. So very basic thing is that you just have 2 buttons like LED, and you just put XOR logical operations. So you put create wire A connected to key 0, wire B connected to key 1, and you can just put this assign to connect keys and LED. So you start from such basic exercises, and then you go through those exercises slowly and run on FPGA board. Then you can also work with the graphics, and in order to work with graphics exercise, all you need to do is that you need to create combinational logic, and then maybe sequential logic to generate color based on coordinate. So this is a fun way of learning Verilog syntax. In parallel with running basics, graphics, music examples, we strongly recommend to run this one homework. So homework is a set of exercises where you don't need a FPGA board and you just need Icarus simulator. This is system Verilog homework. So what you do with this homework, it starts from very simple exercise like this multiplexer question. So here you have example how to implement multiplexer, which is a hardware if. And then you are tasked on how to you have to put here code which implements selection not from 2 pieces of data, but from 4 pieces of data. And once you have this code, you need to run a script. This script checks whether you did homework right. So you just run script. The command Linux is called run Linux Mac sh, and run the Windows is called run Windows bat. And once you run this script, it shows that like everything failed except for first one. So in first one there is already a solution. So when you put a solution, it shows this question as passed. And basically, your first thing what I recommend to do is to go through first exercise. So first set of exercises starts with like a multiplexer question, and there is a test bench. You don't need to look into test bench, which checks whether your module generates the right result. So this is a self-checking exercises. Now, first set of exercises go to one of the easier interview questions. So this interview question is that suppose like we all know how to build like multiplexer from gates, but suppose you want to build a gate from multiplexer, how can you write this code? This was like question popular like 20 years ago, but now like everybody knows this answer, so nobody uses it. It's too like easy screening question. Now, once you do homework on combinational logic, you do homework on sequential logic. And here, there are some exercises which even people with like master degrees sometimes don't do well because they don't train themselves in homework exercises. For example, exercise to like let's go through some of them. So, for example, so this is like easy exercise. Everybody does it well. So you have a module which detects whether in the current clock cycle you have 1 and in previous you had 0, so H. And you need to detect pulse. Now, like another exercise is that here is the code which computes Fibonacci numbers. And like outputs number per clock cycle. Now write a code which outputs 2 numbers per clock cycle. Now, like you need to write serial adder which adds one bit a clock cycle, and you have valid signal which tells it that current bit A and B is valid, and which tells when the current addition ends and you need to start a new addition. Apparently, there are students who don't do this right away, who don't build like serial adder, and who either try to put to collect money like many bits and then to do addition for the whole thing, or don't understand how to put valid. So don't lack basic coding skill. Yeah. Now next. And finally, we go to real like industrial problem, like how to code arbitrary with 2 requests and 2 grants. And this like a realistic problem, because sometimes in hardware we need to for block to share two blocks to share single memory, and we need arbiter to give grants to one of block to share memory. Then next is how to implement a serial to parallel interface, some like gearboxing, and then block how to double number of like tokens in clock cycle. This is something which is useful in credit-based flow control. And so this is like second homework. So I recommend you to concentrate on first and second homework first. And like after this, there is a homework on finite state machine, which uses like arithmetic blocks we just discussed. And then there is homework on pipelining, and with system Verilog, more like advanced features like generate and so on. And then there is a homework on FIFO and credit-based.
Around like somebody.
It's my.
Oh, okay, yeah, okay. So can you hear? Yeah.
Yeah,
Then,
so-
then
Uh-huh.
yeah. So what's your question?
No. It's everything those in the simulator, right? So that's not
Yeah,
on the board.
those are in simulator.
Mhm.
Yeah, they don't require board. So I would recommend to do exercises on a board from a different repository and exercises in a homework from this repository. Yeah.
Okay, thank
Now-
you. Yeah, that's good.
Yeah. And now, last example I want to show is like example with the CPU. So we have some very trivial, the simplest possible CPU, which is the RISC-V subset. And the CPU is just like 300 lines of code, and it has like ALU for like five instructions, and it has control block and decode block, so which just generates bits for control block. And we have register files, so just like array of registers. Now I had a student, I gave a question that suppose you want to add multiplication instruction, and because this is like single cycle CPU, adding multiplication instruction when multiplication is combination is easy. You just add to decoder and so on. But suppose your multiplier has a latency of 2 clock cycles. How do you add? Now, if a student is like every student, figure out how to put stall signal and just stall CPU for a clock cycle. Now, there are some like better students who actually implement pipeline and put forward in this pipeline, so you can mix combinational and pipeline operations in the mix. However, there was a student who, when I ask how to do this student put the following.
Okay.
Okay. So this is funny. So
Mm.
I see. And that one was like all like A grade student or something. So see, they really don't really train many students in like practical exercises.
Well, I guess again, this because most of the students have easy access to software background. They are more for like the single thread execution mindset from day
Yeah,
one.
yeah.
And hardware is like everybody running in parallel, right?
Yeah, and like professors do not, many professors don't do much to break this thing. They just show slides to students. Students go through the slides, and then like professors just ask them to do some straightforward instructions. So here is my code, how to synthesize it with a synopsis. Yeah, so now this is kind of last thing in system. Yeah, so Evgeny, basically, first thing what I recommend you to do is to get get this board exercises, get Harrison, do homework, and after you do this for some time, you will get the feeling how it all works, and then we can discuss what to do next. But
I
it's
have
like
a question.
basic step. Yeah.
Uh-huh. I have a question. So there is a board 20K tank board available to be ready
Yeah.
shipped by
Yeah,
Amazon
yeah, you
Prime.
can
Is
get
it okay?
20K.
Okay, good.
Yeah, for basic exercises it doesn't matter. Yeah, at least right now it doesn't matter. Right now we have everything running smoothly on both tank 9K and 20K. I have a slight preference for 9K because of its layout of pins, but 20K like works just fine.
I can
now.
order both, but because 9K
Yeah.
has a leading time, so that's
Has
gonna
a
be in
what?
December. Long lead time.
Yeah.
So
Yeah, get whatever you can get fast. It doesn't matter. Yeah. Yeah, so you can also use Altera boards, but right now I'm switching everybody to 10 nano boards. Okay, so we will now set board with you. So like also like a final key. So like yeah, a final Cherkashin is actually a well-known person, particularly in ex-Soviet people community, half Russian, half Ukrainian, so I'm connected to both communities, and because the father he was a speaker on some Russian events, so that's why like I recommend him. Yeah. So he is curious about using the thing for like something, so we can discuss the thing. And for you, let's get your board and connect it with some peripherals. Okay. So I will show you what is missing there. Yeah. So now let me just give you what is missing. Oh, did you? Yeah, those two boxes. Okay. So let me just give you what is missing, and you connect it by yourself. So yeah. Ooh. Uh, we need to get HDMI display and connect your board with HDMI display. But I can show you. How I connected it.
I think you need it.
Yeah.
You're
So,
working.
so
It's fine. It's already. I saw that you sent.
No, but also connected to a split.
You did it?
I just practiced. This thing, you can just. I have multiple systems, so like.
Okay, one.
Five stage, five. Myself, something like that.
Yeah.
Now, you also need to connect this. Yeah, so you just like connect the board in this way.
Got this. What's it?
Yeah, this is a microphone.
Keep the repository.
Yes, actually, if you want to get the base, I'm going to because they exactly. This like repository, you just get your you just connect this here.
Okay.
Then you get from, then also you can.
It has
put this
verification
here,
environment.
just sound out.
Verifies every single instruction.
So, and that's it, so you have already created, so now, you, so now what you do is.
This way, it's real fine.
Is this yours?
No.
Okay, so now, what we can do is that we can bring from another room,
It's on, it's like.
using HDMI, just connect your board, see.
Libraries for out, they have Python library. My roommate likes to explain, Gary likes to explain. Talking to the guy, this guy,
Copies.
Huh?
Copies.
you know, his name's David.
Hmm.
You know, he worked for supply book with Sarah.
Mm-hmm.
That's supporting that. This five is like great. I mean, Linux Mint, that's what we're running on Unix workstations. I mean, it's just one library it's missing so far. Maybe that's.
Okay, so now let's put.
Won't be able to running or.
My, it wasn't a computer, it's on a TV. It'd be nice to not be installed. Yeah.
Just put the so you can show it on something because then you can put it.
Yeah. Commercial ones.
Okay. So
Yeah, then you can use
Like
special.
early. Nice to get.
So you have Windows or Linux?
This is the Windows, but I can find at home this Linux.
Yeah.
That might be easier.
Yeah, but we can install everything. So let's put it here.
25 cents.
Okay, so so now we need to put HDMI cable.
Was it used at 25?
Huh?
Gary, wasn't his CPU, it's a 25, right?
Yeah, this board is a Nano 25K. It's a more fancy than 9K. I mean, for like beginners examples, it doesn't matter. 9K is more convenient because it has LCD embedded. Yeah, yes, this is different. I have just a second. Let me give you this.
Okay.
Yeah, so you just connect it here. So let's test
Because you can also.
examples with this board.
Maybe. Yeah. The full environment.
To me, it's interesting, is once you work on Linux, then you have to do the hardware to do.
I can do it. Yeah.
Okay.
Sure. Okay, good. Okay, so now what you do is
Where did you get all these plugins?
this is AliExpress. So if you go to Verilog
Okay.
Meetup website, you can see. Okay, so now what we do is that we are going here. We are going to labs and we are going to graphics.
you're going, for example, to here, choose another FPGA board. So you need to choose board 25K PMOD HDMI. So this
Okay.
is 78. Well, first of all, let me make sure that I got the recent repository. So git pull, yeah, up to date. Yeah, so choose another FPGA. So we are getting 10 primer 25K PMOD HDMI, which is 70. Okay. And now we are doing synthesize.
What would be the advantage?
Oh, but you need to turn this on.
Is this big or is
It was on.
just the pleasure?
Now it's on.
Okay.
Power saving.
Yeah, so let's see. Actually, I don't remember whether I connected this to the left or to the right, but we will figure it out now.
DVI.
Source code. Yeah, it's CGI.
Who funded all this?
Huh?
Like who ran the stuff? You are funding?
Yeah, but yes,
Okay.
yes, I'm fine. Yeah, this, like actually, I went to like education activity back in like 2010. So I was working in the MIPS, and then MIPS licensed some like IP in Russia. So I went there with like a business and then found that they don't have many like educational things. And then some like MIPS was acquired by Imagination. Oh, yeah,
Okay.
it works just fine. So now let's do some game on it. And then some like British company Imagination started to sponsor it, and then like I was going to do seminar, but like after I went to work in the Juniper in 2019, I started to do this just myself as a hobby.
It's a hobby.
Yeah, kind of.
Are you founding some non-profit organization to do this?
So basically, this is like open source project with some people like in different countries who contribute those.
I see.
Like this. So now let's synthesize. Yeah. So this is a game. So now let's check how this works.
It would be interesting to replicate this.
Yeah, you can actually connect camera. If you connect camera to this example, this is actually very important. If you can do this is actually awesome because you need to figure out some platform specific
connection and pin.
Mm-hmm.
I think Huawei, I saw it's got.
Oh,
This is
the book you mentioned that to be published the January.
Yeah.
Is the author UC San Diego?
No, not UC San Diego. Harvey Mudd. Harvey Mudd. It's it's a college in Southern California.
I see.
Oh, it takes so long. Yeah, it's finished.
So the next thing,
Okay, so now here's the game. So now let's. Oh, yeah, you see, you can actually play this game here.
Okay. Okay, here I got it. And this one.
Yeah. But this is his introductory book, and he's publishing sequel. This is his previous.
Oh, okay.
He's actually author of multiple books. Yeah. Yeah, I can actually show you. You can actually browse this book because I have it for review. Just let me show you how it looks like. So if you go to second, so I can you can actually browse this book while like a book is like Pyro and other people. Just a second, documents, pictures, to Yeah, here. So here is a book. So if you go to like FPU,
Mhm.
like here floating point, you can see that it has a very detailed explanation of a floating point. So so this is convenient because it goes into detail. And the CPU is not like toy CPU, but it's like open source project. So due to many open stuff, so let's close everything. Uh,
Oh, maybe.
yeah, we need to close Quartus. Sure, Quartus video application. Anyway, where is? Yeah, here is. So it's 139 pages of floating point law. So this goes through all the details of floating point, microarchitecture, like this and that. The only, and you can even use those blocks to build out of order CPU. We don't need to use them to build fixed pipeline CPU. You see? Yeah, so it shows like microarchitecture. Yeah, you can actually browse it if you're curious. So those are all files for like a review. Yeah, okay. So now you have this working. So there are also exercises with the microphone. So let me show you exercise with the microphone. So with the microphone, it can recognize notes. So in the music, note recognizer or even song recognizer. So you can synthesize. You can synthesize. So then you can sync to the sync and it will show you notes.
Oh, okay.
Yeah, and also there is a sync which allow to play music. With the sync, yeah. But again, generally, this is a good set, and you also can connect LCD to it. I have LCD connector, but I didn't implement support for LCD connector for this yet. Yes. Anyway, so
Yeah, I just ordered a used copy.
what was your desire to use?
Yeah, I want you to. The book is freely available or is you need to, no, you need to pay the.
I guess it's only for him to review.
Oh, okay. Yeah.
Draft.
I can, yeah, because I saw that it's 150 or something like that. Or
Textbook.
when it's published, it's not yet published.
Define my own logic operator. So, for example, I define the logic operator for the.
Knows it's installed, but Wally doesn't.
Puts everything into one.
So how do I pick
All the bits and like, for example, you.
legal search for Wally?
Wait, okay, with its operator. And then using a complex multiplexer that will have two independent control signals that can interfere. Like, for example, one control signal is defining data as class 1. Another one is defining the same data as class 0. There's a conflict between them that needs to be resolved with or something else like that.
You want some like basic combinational logic.
Yes.
Okay. So what you can do is you can so same thing what you do to GP. You get Harris book for reference. You need to read chapter 4. Second, you do homework exercise. If you go through homework exercise, you train yourself pretty well. So what kind of computer is it's like the Macintosh? Okay, let me show you how to run this on Macintosh. Then also you are getting board, comparison to board, but initially you don't need a board. For combination logic, so
Let me show you how to get a homework exercise. So you go to GitHub. And so let's make sure that you do the first exercise now. Then we can do this. Okay. So then you search Uni space Pancho. Git, yeah, Uni space PANCHUL. CHUL, yeah. Yes. Okay, yeah. Now okay, so for some reason you didn't find it here. Yeah, I can actually Google it, not find in the GitHub, not but simply in Google. Uni Pancho GitHub. GitHub. Yeah, yeah, okay, here. So let's go here. So you go to system Verilog homework. You clone this repository. Oh, not fork. Go to no, not fork. Go to code. Go to not here. Person here. Local. Copy. Okay. Now do you have a GitHub installed?
Yes.
Okay, so you need to clone the repository. So now you need to clone it somewhere. Jorge, so here is something which I created to go to next.
That.
So I bought on eBay like 7 cheap computers
Okay.
with everything installed. So basically we are getting a bunch of boards. Everything is installed here, and also those are SSD drives for extra computers. So even if SSD drive not work for them, we can have some minimal number. Yeah, but first I want to test it in like San Francisco or like
Yeah, locally.
locally. Yeah. Test the whole set. And once we make sure that everything works, we can use it there. Also, it's too heavy for the like airplane, but if I go there by train, I like to go to like LA and San Diego area by train.
Mm.
I can just get the train, everything can train.
Did you test the board? The computer's not, it's not, we need to test it.
Yes, we need to test all board. I did test computers and test SSD, but we need to test all boards
Mhm.
for sure before doing this. So we need to test.
And these ones are,
Yeah, those are also I tested, but we need to test them again because what I found is that some combination of this SSD with SATA to USB don't work
oh, okay.
for some reason. Yeah. So yeah, no, like if you sync here to this microphone, so look.
Number.
Now let me show you how.
I see. I see this board. Where did you get this board?
This is also on AliExpress. Everything from AliExpress. Yeah.
Okay.
Everything from
So it's the
AliExpress.
PMOD is the standard interface that you
Yeah, this is standard, but actually I don't like it because all devices with PMOD are more expensive than without PMOD.
Hmm.
So I prefer to buy everything like cheapest possible because this goes to like hundreds of students, and for them I want absolutely minimum price.
Mhm.
So the even like school teacher can buy a bunch of them, just give everybody. Because one thing is when you give to like children something which costs $25, and another $250. You know?
Mhm.
So for this reason, I prefer, yeah, but in this particular case, PMOD is makes sense
Hmm.
because there are just few of them. Now let me do node synthesizer.
Your idea is in San Francisco, you have a location already where we can.
Yes, in San Francisco, there are three persons in their local, like, Hickey Dojo kind of equivalent, so they have some like, place like this in San Francisco, so they want to.
To be teaching there for a day or something like that?
So to like, same thing, so here, when we have this first meeting, there were like 30 people, right? We can make this in San Francisco.
Yeah, because, and I don't know, it's maybe to get in touch with the community college or things like that.
Yeah, they do teach very well in San Francisco City College, so this year, they now teach very well everywhere. If you went to like San Francisco City College, because they didn't teach it anymore.
I think we should set up a nonprofit so people can fund the effort.
Yeah, but right now, the main thing is not really a funding for the things, but the main thing is that getting enough audience, because there is a very strong audience for this thing in Russia, where there are 26 universities are using it right now. So they're making like some seminar every Saturday and doing this. And then there is like in Belarus, in Kazakhstan, Armenia, Azerbaijan, there are some followers, but very few, because they don't have needs to do many like RT and TV engineers. Also, there are some like research in Mexico, so there might be. I have some contacts in like Switzerland and then Brazil, where we can probably make a similar. But the like really strong following is now only like in Russia, where they like people who like seriously solid microarchitecture. So yeah, and like everybody else, I still need to find enough like audience. If there is enough audience, then finding already might be desired, because yeah, certainly places like in Kazakhstan, Nazarbayev University, like they like paid me significant money to go there and make a seminar there. But after this, they didn't follow up because how they explained to me. So they had to have digital design class there just because they have to have. But students graduated, but then don't follow up. Then they go to companies which get like oil and like uranium ore, and there they learn how to use a PLC with CMOS industrial equipment. So they don't need.
They don't even need a PDA.
Yeah, there is a one guy there who got PhD in the UC Santa Cruz, and he just ran there.
Okay.
So he is now trying to set up something there. They do have a PDA for processing signal from like telescope, because they have this like a former like a Russian spaceport of Baikonur. So they have, and also in Kyrgyzia they are using a PDA to process signal from like say something. Those are just small applications. Yeah, but certainly if there is like larger following in countries which need a lot of RT engineers, or which are willing to pay significant money for it, then it makes sense. But now, like apart from like Russia and the Belarus, people are just not interested in working hard on solving macro architectural problems. I mean, they are fine to have some like introductory things like graphical games, but to have some solid following, you need some like people. There are some people online that on this course, and there is even person in Africa, in Kenya, who are working on such problems.
But I guess
This is like small following online.
it's probably because the how to say, the CPUs are becoming
So,
so
I see.
powerful.
So now let's go here.
One
Okay.
earlier that people
Что
have
нужно?
to
Нужно пойти
probably
в
use the power, they go to software, you know,
пойти в
that's why.
если запустить вот этот вот скрипт run Linux Mask. Вот. И после его открыть в терминале, правой
It's
мышью,
less, it's less,
правой
because
мышью
people can easily write a program and running on the side or both.
сделать
Yeah, that's a good question. What is the
The application, right, but the key application that the people want to use, but
that's correct. But it's not can be done with the traditional kind of words, Arduino, Raspberry Pi, or a PC based and use this kind of application. Because finding that is a kind of niche in the security level or in the networking or in the medical devices or what kind of things. I am eager to find that kind of experience because teaching a group of people how to do this thing now is not the issue. It's already a huge amount of, it's already done. The resources to do that. The big question is, okay, and now what I do with that? Why I learn? And that is the kind of how we bring some out.
and also, if you think about it, it's further, there are only a limited number of other companies out there.
Хорошо.
So
Через бью.
the
Сейчас попробуем так.
job
Нажать Enter.
over there, out there, requesting for this kind of capabilities also trying to the software. you request, I mean.
That it's true in some sense, but when you have right now, how many different boards are there? It's about 10 different companies. Then they are selling these things to whom? That's my question. Who is buying that? And why they are buying? Who is people within the company that design the applications? Or there are third-party studio companies that provide the services to build that? And that is not very clear. At least from my point of view, I have not seen that very clear. Who are the kind of companies that are getting that kind of contract to design the things that are going to be used in this technology? Because